Today, we are going to reverse engineer one of the most powerful engines in our local universe, Messier 87. By the end of this video, you will have a complete mental schematic of exactly how a single black hole controls the environment of a galaxy 55 million light-years away. Our canvas is the M87 elliptical galaxy. It contains several trillion stars, but to find the controls, we have to look past that massive outer halo and focus specifically right here on the glowing core. While the physical footprint of this galaxy is massive, all of its sweeping macro behavior is governed by one highly concentrated microengine sitting precisely at its center. Step 1 is defining the weight of this central engine. We're looking at a supermassive black hole with a mass 6.5 billion times that of our Sun. Surrounding this enormous mass is a swirling accretion disk. This disk operates as a feeding zone, actively consuming infalling gas, dust, and whole destroyed stars. But not everything falls in. Twisted magnetic fields thread through this disk. Just before the material crosses the event horizon, these fields catch and funnel a portion of it outward, perpendicular to the disk itself. The plasma caught in these vertical beams is accelerated to incredible speeds, traveling intrinsically at greater than 99% the speed of light. You might expect to see two identical beams shooting in opposite directions, but you only see one. Because the plasma moves so fast toward our line of sight, relativistic beaming amplifies the visible jet and renders the counterjet invisible. If you review the telescope data, you might see recorded speeds of 4 to 6 times the speed of light. This is strictly an optical illusion caused by the extreme viewing angle of the plasma approaching us. This configuration functions as a highly efficient magnetic accelerator. To observe this accelerator, astronomers look for synchrotron radiation. As superheated electrons spiral rapidly along those magnetic field lines, they emit the radio, optical, and X-ray light that our telescopes capture. Looking at the visible exhaust of this system, the prominent jet stream extends roughly 3,000 to 5,000 light-years outward from the core. Along this long filamentary stream, you can identify distinct bright clumps of plasma. These glowing knots are sequentially labeled by researchers as HST1, followed by A, B, and C. Time-lapse observations taken over more than 13 years show these knots moving outward in a twisting, helical path. This precessing motion is driven directly by the underlying spin of the black hole itself. To understand the true scale of what we are observing, we have to look closely at the engine center. Here, the dark central void, the shadow of the black hole, is entirely surrounded by an asymmetrical ring of glowing hot gas. That massive 5,000 light-year jet we just observed truces all the way back down and connects precisely to this highly localized ring. A relatively tiny central point is pushing out a structure thousands of times its own size. This extreme disparity in scale proves the immense density and physical leverage of the engine. The continuous power required to maintain this jet is massive. It carries an energy output roughly equivalent to trillions of nuclear explosions occurring every second. This energy has an immediate local impact. Survey data shows that nova explosions happen roughly twice as frequently in regions immediately adjacent to the jet, entirely due to the intense compression and heating of nearby gas. On a larger scale, we can track this central beam as it strikes the intergalactic medium. As it collides with this surrounding material, the jet expands into two massive balloon-like outer lobes, reaching up to 260,000 light-years wide. These extended lobes act as a massive heat source. They violently warm up the surrounding gas and forcefully expel loose material outward over vast distances. Because this gas is kept artificially hot, it is physically prevented from cooling down, clumping together, and collapsing into new stars. This expansive feedback loop acts as a galactic thermostat. By regulating the temperature of the gas, a single black hole maintains direct mechanical control over star formation across the entire galaxy. Let's review the final assembled schematic. We start at the center with the 6.5 billion solar mass anchor and its twisting magnetic accelerator. Scaling outward, we track the near light speed synchrotron knots as they travel outward along the jet for thousands of light years. Finally, we complete the nested zoom by mapping the 260,000 light-year outer lobes, which actively regulate the temperature and star formation of the massive galactic environment. When we map these mechanisms together, M87's central supermassive black hole reveals itself as a highly ordered cosmic engine. Now that you have the complete schematic, you can review the actual Event Horizon Telescope imagery to see the raw data that proves this engine's existence. These astronomical images now represent the verified components of a fully reverse-engineered machine.